Good morning. Today we will go through the concepts from module 5 about the synchronization. So one algorithm to synchronize the various processes known as semaphores. So using semaphore, you can synchronize various processes. So these are the backgrounds. The processes can execute concurrently, may be interrupted at any time, partially completing execution. Concurrent access to shared data may result in data inconsistency. So earlier we have discussed about the data sharing and inter-process communication and all. But when we are using shared data concepts uh, and also concurrent access, that will lead to an inconsistency in data. So maintaining data consistency requires a mechanism to ensure the orderly execution of cooperating processes. Suppose that we wanted to provide a solution to all consumer producer problem that fills all the buffers. We can do so by having an integer counter that keep tracks of the number of full buffers. Initially counter is set to 0. It is incremented by the producer after it produces a new buffer and is decremented by the consumer after it consumes a buffer. So these are the background. So today we'll go through the concepts of semaphore and also we will just understand the algorithm in a deep manner. And also I will share you the pseudo codes of semaphore synchronization example. You can try in your laptop how to synchronize an process using a semaphore algorithm. So semaphore was proposed by Dijkstra in 1965, which is a very significant technique to manage concurrent process by using a simple integer value. So this integer value or variable is known as semaphore. Semaphore is simply a variable which is non-negative and shared between threads. This variable is used to solve the critical section problem and to achieve process synchronization in multi-processing environment. So these are the classifications of semaphore. We have binary semaphore, then counting semaphore. Binary semaphore means it is also known as mutex lock. It can have only two values, 0 and 1. And this value is initialized to 1. It is used to implement the solution of critical section problem with multiple processes. Counting semaphore, its value can range over an unrestricted domain. It is used to control access to a resource that has multiple instances. So these are the basic classifications of semaphore, binary and counting semaphore. Now, when we are implementing this algorithm, we need to create two functions with a variable s, semaphore variable, and two functions. So these are the two functions, wait and signal. And this is the variable s. We can use it to any name, s or sem. And this using this semaphore variable and these two functions, we can control the synchronization of the processes. So these are the definitions of signal and wait function. Here you can see when this wait function works, what it will do is it will check for whether the variable is less than or equal to 0, and there is a semicolon, means it will stuck here only. After that it will decrement this variable. Now in signal function, it will increment the variable, semaphore variable. So wait function will decrement and signal function will increment the semaphore variable. So this is the basic definition of semaphore functions. Semaphore functions are wait and signal, and variable is s. And when we are implementing the semaphore algorithm, you must guarantee that no two processes can execute the wait and signal on the same semaphore at the same time. Thus, the implementation becomes the critical section problem where the wait and signal codes are placed in critical section. Could now have busy waiting in critical section implementation, but implementation code is short, little busy waiting if critical section is rarely occupied. Note that the applications might spend lot of time in critical section, and therefore this is not a good solution. So this is the drawback. This wait and signal function should not work at the same time. So concurrent working will create an issue when we are using semaphore synchronization. Okay, so this is a simple programming example here. When it is under the semaphore, if the value is less than 0, semaphore value is less than 0. So basically wait signal, one process is entering to a wait signal with semaphore variable. This variable is less than 0. The corresponding process we will put into a list, semaphore list, and will block that process. Now in signal, if that process is entering into a signal, if the semaphore variable, it will pre-increment the variable, here it will pre-decrement the variable. Then it will check for the values less than 0. If this value is less than 0, we will remove that process from the list. So here it will block the process, and here it will remove the wake up the process. So these are the two functions. So we'll watch a video regarding the implementations of this algorithm, and also how the semaphore works in, we can map the working of semaphore synchronization with a real life example. So if you watch those videos, you will understand how the synchronization happens.
Let's go into a little bit more detail of these two functions, wait and signal, and let's see what happens inside them. What is their algorithm? First of all, let's see the wait function. Also, before that, let's see the initial value of s is usually always 1. So we always keep the initial value of the semaphore as 1. Keep that in mind. Now, what happens in the wait function? The wait function actually decrements the value of semaphore. So it decreases the value by 1, right? By one number, one integer number. And after decrementing the value of the semaphore variable, what we do is we check whether, what this function does is it checks whether this semaphore value after decrementing is positive or not. So if it is positive or equals to 0, the process is allowed to use the critical section. So in this case only, the process is allowed to use the critical section. It is allowed to enter in it, and it is not blocked. By saying that it is allowed to use the critical section, we mean that the process is not blocked. And if it is not positive, if it is less than 0, it is negative, then that process is blocked, or we can also say put to sleep. So that process is actually put in that queue we were talking about, the queue which we talked about here, this queue. So this process is actually put to sleep in that queue, which is actually blocked until some other process comes and calls the signal function. Until then, this process is blocked, and after some other process calls the signal function, this process is selected to wake. Now, if you haven't understood this last line, this line until someone does a signal, if you haven't understood this line, ignore it for now and let's understand this signal function. After understanding it, you will understand this line better. Okay, what happens in the signal function? So signal function increments the semaphore variable by 1. And then after incrementing, it check whether the semaphore is negative or equals to 0. If it is, it means that there is some process waiting in the queue. So there are some processes which are in the queue. So if there are some processes which are waiting in the queue, what happens is one process is selected and is waken up, and then the signal returns. And if there are no processes in the queue, that means this is not true. This condition is not true. That means there are no processes which are waiting in the queue or sleeping. Then that signal returns. Now, after understanding it, now you know that this signal function actually wakes up the process. So until someone calls a signal, this process which was blocked is not selected to wake up. Now let's try run these two functions and let's see what happens. So let's say there is the process P1, it came to use the critical section. So when P1 will come, keep in mind the structure of any process that has to use critical section. This is the structure. Any process that has to use critical section will enclose the critical section in wait and signal. So what that means, it will call the wait function first, and after using the critical section, it will call the signal function. So keeping that in mind, when P1 comes, it will definitely call the wait function. When it will call the wait function, it will as semaphore variable will be decremented. So right now the value of semaphore is 1. So after the wait function was called, its value became 0. Now let's see when the value becomes 0, let's see if this condition is true or not. If the value is positive or equals to 0, process is allowed to use the critical section. So in this case, this condition becomes true. When it becomes true, this process P1 is allowed to use the critical section. So it will enter in the critical section. Now P1 is using critical section. Now let's suppose another process P2 comes along to use the critical section. So let's write P2, and when it will come, it will again call the wait function, right? So when wait function is called, s will be decremented. Right now s equals to 0, so it means the s will become minus 1. Now when s becomes minus 1, let's again check this condition. Is it true? Is s greater than or equals to 0? No, this condition is now false. When this condition becomes false, it means this is true, obviously. So when this condition is true, when s is negative right now. So when this condition is true, then that process is blocked or put to sleep. So P2 will be blocked, it will be put to sleep in the queue. Now this process is actually blocked and it's waiting for the critical section to get empty. Now let's do it one more time, and let's suppose another process P3 also comes, so that you will understand better. Let's take this process. Let's take the example of this process too. So when P3 comes again, wait will be called and S will be decremented. Since it is -1 now, it will become -2. Again, after it becomes -2, this condition will be checked and obviously it is false. This condition is true. Again, P3 will be blocked and put to sleep. So these two processes are blocked right now and they are waiting for this critical section. Okay, now let's say P1 has done its work, and when it will get out of the critical section, it will call the function signal. So when signal will be called, S will be incremented by 1. That means S is right now -2, and when it will be incremented by 1, it means it will become -1, right? And then this condition will be checked. If S is less than or equals to 0, it means some processes are waiting, and -1 is less than or equals to 0. This condition is true right now. And when it's true, we know some processes are waiting, and you know that P2 and P3 are waiting in the list. So when this condition is true, what happens? One process is selected and waken up, and then the signal returns. So this function, this signal, will wake one process up to use the critical section, and then it will return. So P1 has done the work, it's gone now, and now P2 is selected to use the critical section. So P2 is now using the critical section. And then after P2 is done too, it's done its work, again P2 will call the signal function. It will increment S by 1. That means now, since S is -1 and you increment it, it becomes 0. Again, this condition is checked. If S is less than or equals to 0, if this condition is true, and we know this is true, S is 0 right now, it means again some processes are waiting, and we know P3 is waiting. So it will be selected and it will be waken up, and then the signal will return. Now P3 is selected and P3 is now using the critical section. So let's say P3 has done its work too. After completing its work, P3 will call this function signal and it will increment S by 1. Now let's increment 0. So when we increment it, it becomes 1. Now let's check this condition. This condition will be checked. Is semaphore less than or equals to 0? No, this condition is false now. Why? Because S is positive now. This condition does not hold true. So when this condition is not true, this means no process is waiting. So the signal will return. Right? So this is how this all will work. Let's now cover the implementation of semaphores. To implement semaphore, I have divided it in 6 steps to make it easy for you. So follow these 6 steps and you can easily synchronize your code using the semaphores, a semaphore variable. Okay, the first step is include the library semaphore.h. So you don't have to write the functions wait and signal all over again yourself. You just have to call them, and they are written in this library semaphore.h. So the first step is include this library semaphore.h. The second step is you have to declare the semaphore variable in a place accessible by all the processes, or if you are performing synchronization between threads, then all the threads. And this is the reason I asked you those 2 questions in the previous video. So you have to do that. And the third step is initialize the variable, the semaphore variable. To do this, we have a function which is known as sem_init. We will see it in detail in the next slide. Okay, after doing that, after all your work is done, at the end of your program, you have to destroy the variable. So actually, this is the these are the steps of your main program, and these 2 are the steps that are done in the processes or the threads. So in the process or in the thread, you have to make sure that wherever you use the critical section, call wait operation before it and call signal operation after it. So the function calls in the library semaphore.h for the wait operation is sem_wait, right? And the function call for signal operation is actually a little bit different. It is sem_post. Now let's discuss this third step. The rest of the steps are easy. We'll see them in the code, but we must see this third step, initialization of the variable semaphore. Let's see that. To initialize, we use this function sem_init. It has 3 parameters. The first parameter is the address of the semaphore variable. So here you can see The data type of semaphore variable is under sem underscore t. So you will write sem underscore t, and let's say we call it s. Let's say we call this variable s. So you will pass the address of this variable s to this parameter here. That means you will write it like this: address of s, not x, address of s, since we have called it s here. Now ignore this for a second. The third parameter is the initialization value of s, that with which value you want to initialize it at first, and we talked about it. We initialize it with 1. We talked about it in the previous videos. So initial value is 1. Now let's come towards this p shared. What is p shared? The value of p shared is 0 if we are performing synchronization between the same process, or in other words, between different threads. So we covered this in the last week, that threads are sub processes or divisions of one process. So if we are performing synchronization between threads, it means we are performing synchronization between one process. And if we are performing synchronization between different processes, the value of p shared is any value other than 0. Also, the function sem underscore init returns an integer value, and it returns 0 on success and -1 on error. Now let's see. Okay, so this is the example of synchronization of two threads. Let me change the color of my marker since red is already used here. Okay, so this is the step number 1. This right here is the step number 1. So what was the step number 1? It was to include the library semaphore.h. The second step was declare the semaphore variable in a place which is accessible by all the processes or the threads. Since in this example, we are performing synchronization between two threads. So the place which is common or accessible by all the threads is a global variable. So a global variable is actually accessible by all the threads of a process. We studied that in the last week's videos, in the last week's topic. When we were studying multi-threading, we studied that. So I have declared the semaphore variable as a global variable, and we talked about it, that the data type of semaphore variable is sem underscore t. So sem underscore t, and I have named it mutex, right? Just for fun, I have named it mutex. This is the second step. Okay, one more thing. This variable char buff with a size 40, this is actually my critical section. What I have done is I have used an array with the name buff, and I have declared it in a place which is global to all the to all the threads. So since it's global, it means any thread can access it. When any of the thread can access it, that means it is a critical section. So any of the threads can use it at the same time, and I don't want that. So this is actually my critical section. And this is the prototype of the two threads, the function of two threads. Okay, now let's see. This was the first step. This is the second step. Now let's go towards the third step. The third step was initialize the semaphore variable. So this is the initialization part. The first parameter was the address of semaphore variable. This is our semaphore variable mutex. So we have written address mutex. The second variable was p shared, and p shared variable is 0 when the synchronization is done between threads. Since we are doing it between threads, we have written it 0. And the last parameter is the initial value of semaphore, and that is always 1. So we have used 1 here. Now here I have created two threads, and we covered this last time, so I won't go into too much detail. But these are the two messages of the threads, first thread and second thread. I have made a character pointer message one and just save these strings in it. Now here I have created two threads using the function pthread underscore create. So this is my thread 1, this is my thread 2. I have passed the function write buff to thread number 1, and I have passed the function read buff to the thread number 2. Okay, you can assume what's happening here. You can easily guess. So what I'm doing is the first thread will write in this variable buff, in this character array buff, and the second thread will try to read from it, and I have to make sure that they don't do it at the same time. So since I have created them, and you know that when threads execute, they run parallelly. So when they are running parallel, they both will try to use this critical section at the same time, and I have to make sure that they don't do that. So let's see the next part of the code. Okay, also the fourth step was to destroy your variable mutex, your variable semaphore, but make sure that you do it just before return 0, so that you are not destroying it um, before the critical section is even being used. So don't do that. So just do it at the end of your program. Now let's see my two threads. This is my thread number 1. This is actually the function of my thread 1, and this is actually the function of my thread 2. I have said it the other way around. This is actually my thread 1 and this is actually my thread 2. I said the opposite before. Okay, now let's see. In the function write buff, remember the name of my critical section? It is buff, buff. So in it, where are we using the variable buff? This is where this line s printf, this is the line where I'm using the function, the variable buff, which is actually critical section. So I'm just writing something in it. I'm just writing hello 6th semester in it using the variable sprintf. So this is my critical section. I have to call the variable, the function sem_wait before the critical section and sem_post after critical section, and this is how we do it. So I have called sem_wait before critical section, and I have passed it my variable address of my variable, my semaphore variable, which is mutex. And similarly, I have called sem_post after critical section and passed it the address of my semaphore variable mutex. Now let's see my second thread. So what I've done in the second thread, I have used the critical section buff and I have just printed this array on screen. Now, when I'm using it, I have to call sem_wait before and sem_post afterwards. So exactly like I have done here. Now this is the whole code. This is very, very easy. Synchronization through semaphores is very easy. This is the whole code. Now let's see the output. Let's see whether we were successful while synchronizing the two threads or not. Let's see that. And before seeing it, keep one thing in mind. I have created thread 1 first and I have created thread 2 afterwards. Let's see the output. Okay, here I have compiled my code and I have run it. There is one more important thing. While using semaphore library, you also have to link it with the LP thread like we did it last time. You also have to do that. So we're not just doing it because we are using threads. Even when you will do synchronization, you will perform synchronization on different processes. You will again write -lp thread to compile the library semaphore.h. Now let's see, when the program ran, it showed in main thread after creation of threads, and also both threads are running in parallel. Also, one more thing, I made a few modifications in terms of just more printf lines in the code so that you will understand it better before showing this output in the previous code. Now what happened is second thread got the CPU first and second thread started first. So second thread, thread 2, entered the critical section first. So that's why we are seeing this line, thread 2 entering critical section. Afterward, first thread also started. So right now second thread hasn't left the critical section, but first thread has started. And it will also attempt to use the critical section. So you must notice that after the first thread started, it tried to attempt the critical section at once. So you must see thread 1 and a line like this, thread 1 entering critical section. You must see it here, but you are not seeing it. Why? Because first thread is actually blocked. So until thread 2 leaves critical section, thread 1 cannot enter. So you can see when the line appeared, thread 2 leaving critical section, then thread 1 actually entered the critical section. So it was actually blocked. So after thread 2 left, then thread 1 entered and then it left. Otherwise, if it was not blocked, this line here, what I'm trying to say is if thread 1 was not blocked, then this line here must have appeared right here. And it didn't. So that means it was actually blocked until thread 2 left critical section. So when thread 2 left, then thread 1 entered the critical section. So we can see that we were successful and they both are not using the critical section at the same time.
And when we implement the semaphores, we have some real life problems, they can be used to solve any of the traditional synchronization problems, but semaphores are essentially shared a global variable. In our algorithm, it is S, so can be accessed from anywhere. So it will create some issues. There is no connection between semaphores and the data being controlled by it. There is connection to the data used for both critical section and for coordination. No control over their use, no guarantee proper usage. So apart from semaphore, we have another algorithms are also available for the task and process synchronization. So that we will discuss later. Thank you.